Hi guys, today we're going to be doing some examples from 2.4 for general solutions of trig equations. So it's from your Jacplus textbook, but I've also got an example from Cambridge, which will be the first one. So I wanted to do one for sine, cos and tan. So I'm going to start with sine and let's have a look. So it's sine, I'm going to rearrange this, divide by 2. So I'm going to get sine x equals root 2 on 2. And look, this is where you might be confused because, well, we do not have root 2 on 2 in this table of exact values, well, anywhere, let alone in the sine column. But of course, if you were to multiply by root 2 on root 2, i.e. you were to make the denominator irrational, you're going to get 2 on 2 root 2. And of course, that will be 1 on root 2. So actually, root 2 on 2 is 1 on root 2, and you may benefit from writing that in the table of exact values, putting a rational denominator if you so wish. However, it is pretty easy to move it around. So I'm going to write sine x equals 1 on root 2. So I'll get rid of that. And let's just change that to 1 on root 2. Now, we're making a general solution. So essentially we're making a formula so that we can find any solution for anywhere around the unit circle. So you could go 100 times around the unit circle and you'd be able to find the value of x there. So look, let's draw the unit circle and let's draw what we need. So here is our right angled triangle. And the sine value, which is the height of the triangle, that is 1 on root 2. And let's just put the 1 there. So that's 1 on root 2, that height there. And then if we look in our column for sine, we can see that that's pi on 4. So pi on 4. And of course, you could do this in degrees as well. I'm going to do it in radians. And it doesn't actually tell me to do it in radians here, but I'll do it in radians. So now we can say, well, sine is positive here. So we're going to get the solution for this height of our triangle being positive in quadrant 1. But we're also going to get that in quadrant 2. So that pi on 4 here. And of course, the height is going to be 1 on root 2 as well. And it's also positive. So we have two places where we can get 1 on root 2 as our sine length of the triangle or height of the triangle. So what we're going to do is describe those two places. So I might do one at a time. So I might just get rid of this one for the moment. And let's concentrate on the first case, so in quadrant 1. So I'm going to get x equals pi on 4. And then I'm going to say, well, if I want it to go around the circle again, so there's pi on 4, and we'll go to there. If I wanted to go back to that place, that same stick, that hypotenuse of the triangle there, then I would be adding 2 pi. So I could say plus 2 pi, and I would get the same, the same place like that. I would also get it if I did pi on 4 plus 4 pi. So that would mean I go plus 2 pi, and then I go around again, 4 pi. And then I'd get it if I said plus 6 pi or 8 pi or any multiple of 2 pi. So what I do to represent the number of times I'm going around the circle, I call that n. And I can say, well, n is the number of times around the circle. So you don't need to write that. I'm just putting it there so you realize what I've done there. So now I want to neaten it up and I want to make it in a form where it's easy to sub in values. So if I say I go twice around the circle, n would be 2. If I go in the negative direction 3 times, n would be negative 3. So what I'll do, I'm going to put a common denominator there. So let's say x equals, and we can see that there's a denominator of 4. So let's multiply by 4 the top and bottom of this 2 pi n. And I'm going to get x equals 8 pi n plus pi on 4. And even nicer is if I go like this, 8n plus 1 pi over 4. And then you see any value for n that I sub in, just say I sub in a 3. 8 times 3 is 24, plus 1 is 25, so 25 pi on 4. So you get the solution really quickly and easily there in a form that's really nice. So that's that's part of my general solution. So I can work out any time that my hypotenuse of my right angled triangle is in quadrant 1 when my angle is pi on 4. Or when my sine length is 1 on root 2. But what we also need to consider is in quadrant 2. So we already have established that sine is positive here. So I'm going to put that and 1 on root 2. That's that length there. And here is pi on 4. Now notice that in you can have different ways of expressing the same thing. So in this case, I'm going to measure this angle like this. So from 0 over to here. But I mean, you could measure it in the negative direction like this. So if I'm going in the positive direction, I'm going to be, well, here is 4 pi on 4. So to here would be 3 pi on 4. 4 pi on 4 minus pi on 4 is 3 pi on 4. But you could also say, well, it goes negative 4 pi on 4, negative 5 pi on 4. So you could call that angle negative 5 pi on 4 and you would get to the same stick. So it doesn't matter which one you use. I'm going to use the positive, and generally speaking, I use the positive mostly. So here I'm going to say x is going to equal, well, 3 pi on 4. And if I wanted to get back to that same place, I would add 2 pi, or I could add 4 pi, or I could add 6 pi, or 8 pi, etc., etc. So I'm going to say plus 2 pi n. And once again, let's make it look neat. So x equals, let's times by 4 on both the top and bottom. So it's going to be 3 pi plus 8 pi n on 4. And now I'm going to get x equals, we've got 3 plus 8n pi on 4. And look, you can say 8n plus 3, or you can say 3 plus 8n, it really doesn't matter. So I'll leave that like that. So there is my second general solution. So what we see when we use sine, you'll start to notice that we've got two distinct general solutions. Two distinct general solutions, and that's because of the location of sine being either positive or negative, where it is in the unit circle. Let's move down and we will look at the next case, and this time we're looking at cos, and here they're asking us to actually find the solutions using a general solution. And when we use general solution is where we need to find quite a number of solutions. It's really quick and easy. So here I'm going to undo this again, so I will, this here, so I'm going to say 2 cos 2 theta equals root 2. So I'm just, I've just added root 2 on both sides, and now I'm going to divide by 2, giving me cos 2 theta equals root 2 on 2, which again is 1 on root 2. So the same deal as we look up into the table of exact values. We don't have root 2 on 2 in this table of exact values, it's 1 on root 2. And it's still pi on 4, and we need to recognise that it is, just the rational denominator there. So same idea, pi on 4. So let's draw a picture of that, and I'm actually going to say let z equal 2 theta, therefore cos z equals 1 on root 2. So here we go. And here we have pi on 4. And cos is this length here. And now I'm going to deal with this for a start. So I'm going to deal with quadrant 1. So cos is positive in quadrant 1. We also know that it's positive in quadrant 4, but we'll get to that in a minute. Let's do one thing at a time. So our first value will be, well, pi on 4. Z equals pi on 4. And again, if we want to get round to that place again, well, we would be saying plus 2 pi. And if we wanted to go around again, well, it'd be plus 4 pi, plus 6 pi, plus 8 pi. In the negative direction, minus 2 pi, minus 6 pi, minus 8 pi, whatever. So it has to be a multiple of 2. And for that, we put n. And what I should have written in the previous example, I'll just go back, is n is an element of z, and z refers to integers. So n can be 1, 2, 3, negative 1, 2, 3, whatever. It's not going to be fractions or decimals. And the same thing for this one. So where n is an element of z, z referring to integers. So let's see, here I have z is pi on 4 plus 2 pi n. So now remembering that z is not what we want to deal with, z is actually 2 theta. And look, in this case, it's not too difficult, so you probably could get away with leaving it as 2 theta, but for the sake of being, the same all the time, I'm going to always use the z. So let's times by 4, we get pi plus 8 pi n on 4, and then I'm going to divide by 2 on both sides. So that can be theta equals pi plus 8 pi n over 8. And well, now I can just go, well, theta equals 1 plus 8n pi over 8, where n is an element of all integers, and is an element of z. So there's our first general solution for our cos value there. And we've still got one more to go. So let's look back at that. And we see where else cos is positive, and of course it's in quadrant 4, so just there. And in this case, this is one where I will use the negative angle. And you'll see, as you get used to these, you could just do plus or minus pi on 4 for your two angles, but I'm going to do them separately, so you can really see how it works. So in quadrant 4, we've got z, so cos z, and we let z equal to theta. So z equals negative pi on 4. And remember that, well, if we're here and we want to get back there, we could go like this in the negative direction. So you could write minus 2 pi n if you wanted to, but the more conventional way to go is in the positive direction, because you can sub a negative value for n. So if you want to go in the negative direction, n can be negative 1 or negative 2 or negative 100. So it's better and the usual thing to write plus 2 pi n. So notice, to get to that stick again, that hypotenuse in quadrant 4, we need to add 2 pi. So let's common denominator it again, times 4, and we get z equals neg pi, I might write it around the other way around, so 8 pi n minus pi over 4. And then of course, well, z is actually 2 theta. So now I'll divide by 2 on both sides, so theta equals 8 pi n minus pi over 8. And then, well, let's make that look a little nicer. So we're going to get theta equals 8n minus 1 pi on 8. And again, where n is an element of integers. So these are our general solutions. And in this part of the question, they're asking us to find the general solutions from, I think, negative pi to pi. Let's just double check that. Yeah, from negative pi to pi. So we want to find the value of theta from negative pi to pi. So we've got a domain. So we're going to use these two general solutions. So what I like to do, I'm just going to scroll over here. I like to set up a little table, and I've got values for n, and then I've got my two general solutions. So 8n minus 1, 8n plus, yep. So 8n plus 1 pi on 8, and what was it, 8n minus 1 pi on 8. So these are my two general solutions for theta, and now I'm going to apply them by subbing in values of n. So 0, 1, neg 1, 2, and neg 2. And look, I'm going to do all of those, even though some of them will be outside the domain, just so you can get the hang of how it will work. So if I sub 0 in, 8 times 0 is 0, plus 1 is 1, so 1 pi on 8. So that's one solution I could have. That works. Our domain is from negative pi to pi. Now I'm going to sub it into the other one as well, so you need to do both. So now we've got 8 times 0 is 0 minus 1, so it's negative pi on 8. That works. And make sure as you do it, you do in pairs 1 and negative 1, 2 and negative 2. The next would be 3 and negative 3. You want to do 1, 2, 3, 4, 5, and then find, you miss out your negatives, or vice versa. So now theta is going to be 8 times 1 is 8 plus 1. 8 plus 1 is 9 pi on 8. So that's too big. But as I said, I'll go through them all just so you get the hang of it. Now we've got 8 times 1 is 8, minus 1 is 7. 7 pi on 8. That works. Negative 1, 8 times negative 1, negative 8 plus 1, negative 7 pi on 8. And you can see that even though the positive one didn't work, we still have to continue with the negatives because there might be a negative that works. I know that 2 is not going to work because if 1 didn't work, it's too big. 2 is also going to be too big. So that would be 17 pi on 8. But of course, I don't need to check that because I already know that 1 didn't work. It was too big. So let's go on the other side. So negative 8 minus 1 is negative 9 pi on 8. So that's too small. So now I know that any negatives are not necessary anymore. So I wouldn't need to do that. And look, I'm just going to leave the dash there because if I was doing that, I wouldn't do that either. Before, positive 1 worked. So I'm going to try positive 2. I have a feeling it'll be too big, but we'll see. 8 times 2 is 16, minus 1 is 15 pi on 8. And of course that's too big. So now we know that we've done enough. Of course, negative 1 did work, so I probably should do negative 2 as well. 8 times negative 2, negative 16 plus 1, negative 15 pi on 8. So that doesn't work. Too small. So once you've got a cross for a positive number, then you wouldn't be going further with positive numbers. Once you've got a cross for a negative number, you wouldn't be going further with negative numbers for that equation. And the same thing on the other side. So once you get the cross for positive, don't do more positives. Once you get the cross for negative, you don't do more negatives. So our solutions within the domain would be those 4 there. All right, final one, and this is a tan example. So let's scroll down. So find the general solution of the equation tan x minus root 3 equals 0. So this one, so this time we've got a unit circle like this. And tan is a bit interesting, and we can see, well, this is going to be tan x equals root 3. And again, as I keep saying, you want to know the unit circle, not the unit circle, the table of exact values. So make sure you can derive it so that you can write that out really quickly, because you want to be able to refer to it. You don't want to have to memorize every value off the top of your head. You want to be able to write it out and then be able to refer to it there. So tan root 3, that's pi on 3. So back we go, and let's draw that. So pi on 3. And tan is positive in this quadrant. So like usual, I'm not going to illustrate tan because people find that a little confusing. Tan is sine over cos, so the sine and cos are both positive in quadrant 1. That's why tan is positive. So let's see. There is tan, and we can say, let's make a general solution for that. So we can say x is going to be pi on 3. And let's see what happens here. If I want to get back to that stick, I would add 2 pi n. But there's something interesting about tan, and this is also when you sketch tan functions why the period is pi, not 2 pi. So now tan will be positive here, so pi on 3. So what we can do, instead of putting 2 pi n, you can do 2 pi n, and then you would have 2 general solutions for tan. You could, but it's a bit of a waste of time, because if you think about it, to get from this stick to this stick, look at that, that's a straight line. That's 180 degrees from there to there, or pi. So actually, for tan, we have 1 general solution. And I should have mentioned for cos, we have 2 general solutions, but they are quite similar. And as you get used to it, you'll see that as you go. Sine, 2 distinct general solutions. cos 2 general solutions and tan just 1 general solution. So as I said, if you want to do 2, you can, but it's going to be more work. So x in this case is going to be pi on 3. And then to get to the next one, we're adding pi. To get to the one after that, we add 2 pi, 3, 4, 5, 6, 7, and we keep going around, so on and so forth. So we're adding pi, and the number of times we go around the circle in the positive direction is a positive n value, in the negative direction is a negative n value. So we can say plus pi n. Let's make a common denominator, timesing the top and the bottom by 3. So that's going to give us pi plus 3 pi n over 3. And well, then we can get x equals 1 plus 3n pi on 3. And in this way, you can find any of the solutions just by subbing in values for n. Again, I'm going to say n is an element of z, so integers there. So we're not getting fractions or surds or anything, we're just getting whole numbers for n. All right, that completes the examples from the book and really a basic set of cos, sine and tan general solutions.